All right. First of all, hello sir and hello everyone. My name is Pavini and my roll number is 13840. And today I'm gonna be presenting about the introduction to ring. That is the first topic of our course. What is the definition of ring, example of ring, property of ring, and the subring, what is the subring, and any special in that we will cover in this presentation. Now look, we would start together. This is my content that I would like to present today. The first thing is I would like to review about the group, what is the definition of group and some example of it also. And the second part is ring, the main topic of our presentation today. And ring definition, yes, ring example a bit included in here. And the third part is about the property of ring, what is that property of ring, we include it all. And the rule of multiplication are also included and with proof also. And uniqueness of unity and inverse, yeah, I also included. And the first part is about the subring. It is also important in this video. I will like about describe about definition of subring, and I would include about subring test also, example of subring, all in there. Now we would like to start about reviewing about the group. I suppose most of you know about the group. Now let's start with definition. Suppose we have the set G, and together with a binary operation, only one binary operation, it can be multiplication or it can be addition. In here I specific about multiplication, and you can see it can be addition also. Yes, no problem. Both two operations can be used to create the group that assign to each pair of element AB in the group G. So the element of the group G is denoted by AB. In here is what? In here is under multiplication operation. Yes. Suppose if we want to do in under addition, so in here is A plus B. So it is called under addition. So we say that G is a group under this operation. And then it follow the three main properties that are satisfied. Actually, there are so many more properties than that, like closure under addition, closure under multiplication, identity, inverse or something, commutative. That is called, all of them is belong to the property of group also. But there are three main part of them. The first one is associativity or association. This is what the operation is associative. We can write it is the brackets AB times C is equal to A times bracket BC. In case this one is in case of multiplication, as I said. How about addition? Addition quite similar. Let's see. Suppose we have ABC, yeah, in the group G the same, and A plus B plus C is equal to A plus B plus C. This is called associativity under addition, and this is called associativity under multiplication of the three elements of the group G, A, B, C. Now we continue about the second property. It is also important about the identity. Yes, I think most of you know about the identity. What is the identity? Suppose we have an element E that is called an identity in G. Then we can write in such a way A times E equal to E times A equal to A. That A also belong to G. Then it is called identity. It means that there is no change if we do multiplication E with any other element in G also. There is remain the same element, no change. Suppose we gonna be study about under addition, identity under addition. Suppose we have E the same plus A, an element or the element A belong to G, that it is commutative, yeah, group is commutative, plus E is equal to A. It is remaining the same element. Normally, under addition, the identity mostly is 0, yeah, can be 0, and under multiplication it can be changed. It depends on the group. Now we would like to consider about the third property. The third property is inverse. What does it mean inverse? Suppose we have an element A belong to G, and there is an element or the element B also belong to G, but B is called an inverse of A. If we can write in this form, mean A multiply A times B equal to B times A equal to E. E is what? E is identity. Yeah, we discussed this part. E is identity. So this is under multiplication. Inverse under multiplication. How about inverse under addition? What it could be? Suppose we have an element, then the inverse of A gonna be minus A. It's equal to identity is mostly 0. Yes, this is called inverse of an element A under addition. Now continue to the next part. Okay, the next part is we're talking about the example of the group. In here, most of the group that I have been mentioned in here mostly have been used in normal way, yeah, like Z under addition or under multiplication. So I would like to explain it step by step. The first example is Z under multiplication. It is the notation of the group, brackets and a Z and then operation. It can be multiplication or it can be addition. In here, Z under addition. Yeah. And here is what an element. Suppose we have an element A, B belong to Z. Then the group is the form of under operation addition. Now equal to we have A plus B. Yeah. This is form the group of integer under addition. Now we continue to the next example. Let me clear this first. Okay. Now the next example. Next example, all star. All star representing about a real number, but not including 0. Yeah, a real number is non-zero element. So this is the group of non-zero element of real number under multiplication. Yeah, just it quite similar. Suppose we have an element A, B, that A, B not equal to 0, then under multiplication A times B equal to B times A. Yeah. In real number, it is commutative. Then I can write like this. Now continue to the next example. Group of integer modulo n under addition. Here is Zn mean the integer modulo n. Suppose we have A mod n. Yeah. A is what? A belong to Z. Very quite simple. Any element, it is the remainder after modulo n. The answer is the remainder after we modulo with n. Now continue with the next example. The next example is similar to the previous example also, but in here it is the unique modulo n. Unique is what? Mean non-zero element integer. Mean non-zero integer modulo n under multiplication. Non-zero integer modulo n, and the multiplication. Now we continue to the next example. I think maybe most of you know about it. It is G and R, mean general linear group of n cross n matrix over real number, mean n3 is belong to real number. Suppose G 2 R mean what? Its element 2 cross 2 matrix, and the coefficient not coefficient, the n3 is belong to real number for A, B, C, D. This is the collection of that form, the set of this form, this matrix 2 cross 2. This is called group, general linear group of 2 cross 2 matrix over real number, that A, B, C, and D belong to real number. Okay, now I think maybe you clear about that. Now we continue to the next example, the last example that I included today. It is the UN. UN is what? It is the group under multiplication modulo n. Like suppose we have U10. I think most of you know about the Cayley table. Cayley table. Yeah. This is modulo 10, mean multiplication and then modulo 10. This is the ND. This is the ND, the element, and then multiplication of them, and then we use mod with n. The remaining part is the element of U10. Okay, now I review the group just right here. So we continue to our main part about the ring. Okay, continue to the ring. The first thing is ring definition. So we continue with the ring definition. Suppose we have a non-empty set O is called a ring if the binary operation under addition and multiplication are defined in O, and these four properties are whole, then we can say O is a ring under binary operation under addition and multiplication. The first property is abelian group. Suppose we have a group O under addition. Yeah, we have discussed above. It is an abelian group. This group is abelian group, mean the set O under any operation under addition operation can be write like this one. I will explain you what is the abelian group mean. Abelian group here mean we can write an element of, suppose we have A, B belong to O. Then O, sorry, not O, this one. O, then O is a abelian group if we can write A plus B is equal to B plus A. Is it called what? Is it called commutative law? If the commutative law hold in O, then O we can say is an abelian group. Okay, the second property is closure under multiplication. Closure under multiplication means suppose we have two elements of O, then the multiplication, both of them still belong to O, then O is called closure under multiplication. Okay, I hope you clear about that. Now we continue to the third property. Third property is association or associative law. In here I used to study about under multiplication. We can say the operation is satisfied with association. It is writing in form. Suppose we have three elements A, B, C belong to O, then A times bracket BC equal to bracket BC times C. Sorry, bracket BA times C. In here is what? Under multiplication. How about addition? Association law also is quite similar. Suppose we have an element A, B, C belong to all the same, and the association is held by A plus B plus C is equal to association. We change the bracket A plus B plus C. This is called association with operation addition. This is multiplication. Yeah. This is quite simple. This is just the basic of algebra that I think most of you know about that. Now we continue to the next property, the first property, distributive law. Distributive law have two parts, left distributive law and right distributive law. Here, let's see. In this form, A into B plus C, we can use distributive law. We get AB plus AC. This is called left distributive law because A is on the left side of addition. In here is called right distributive law. So A plus B times A is equal to BA plus CA. This is called distributive law on the right side. Okay, I think most of you clear about that. And one more important thing, the property not just okay. You can satisfy with these four property and the non-empty set all under addition and multiplication. Then this is called ring. Now would like to get some interesting difference between ring and group. Ring and group. Ring, the notation, suppose we have all under multiplication, under addition, and group, suppose we have all set all also. It's only multiplication or can be addition. Here is the difference. The difference between ring and group is ring using binary operation, two binary operation. One is under addition, one is multiplication. But group is only one operation only. It can be addition and it can be multiplication, only one over the one set, only one. The notification of the group, and the two operation we can call the ring. Yes, I hope you clear about the ring and the definition and the property. So now let's start with some example. Okay, some example of the ring. Here's the example. The first example is the set of integer under ordinary under addition and multiplication is a commutative ring with unity. We know that suppose we have an element A, B belong to Z, then A plus B equal to B plus A. Yes, it is true in general. Suppose we have 2 plus 3 equal to 3 plus 2 equal to 5. It is the same result. It is commutative in addition. How about multiplication? Suppose we have 2 times 3 equal to 3 times 2 is equal to 6. Yes, this is called commutative ring. And with unity, yeah, we already discussed what is the unity. Unity means if we say in case of multiplication, suppose we have an element 1 times any element of A equal to a times 1, it remaining to be the same a, where a is belong to z integer. And yes, this is under multiplication and under addition. So now we move to the next example. I hope you clear about it. Next example is Zn, mean the integer modulo n under addition and under multiplication. It is the commutative ring also. So we have here is an element 0, 1, 2 until n minus 1. And we used to say both have 2 times 3. Yeah, 2 times 3 equal to 3 times 2 equal to 6. But modulo and yeah, that's it. This is abelian. Yeah, we can say it is abelian group because it is the ring. And with unity also 1. Here is the unity. Okay, now move to the third example. The third example is the set of polynomial. Set of polynomial set of, it form like we can say ax power n plus a1 x power n, a2 x power n minus 1 plus dot plus an x power 0. Yeah, this is form of polynomial. Now the polynomial zx with variable x with coefficient, integer coefficient y, because this belong to z. Every coefficient is always integer, and this is also under ordinary under addition and multiplication. We know that the ring have two binary operation under addition and multiplication, and it is also commutative ring with unity f equal to 1. Suppose we have x squared plus 2x plus 1 times fx, mean times 1, fx equal to 1. It's gonna be remaining the same, x squared plus 2x plus 1. That is called identity. Now we move to the fourth example. The fourth example is talking about the matrix 2 cross 2. Here is the matrix 2 cross 2. We denote it by m2z with n3 belong to a, b, c, d belong to z, mean integer. Each entry is integer, is non-commutative ring with unity. Why is non-commutative? Yeah, let's say example like 2504 multiplied by 101, it's equal to, it is 2, this is 2 plus 5, it's 7. Now the next is 0, 0 and 4, 0, 0, and the next is 4. How about we change we put 1101 multiplied with 2504. Will the result is the same? Yeah, we multiply it. 1 it can be 2, yes. Yeah, this is 115. 5 plus 4 is 9, and this is 0, this is 4. Yeah, the result is not the same, so that's why it is non-commutative, but unity is exists. And here is 1001, mean suppose we multiply 1101 into identity, mean unity 1001 it's gonna be the same 1 1 0 1, no change. It's called identity of matrix 2 cross 2. Now we move to the next example. Example number 5. 2z mean even integer under operation addition and multiplication. It is commutative. The element of 2z it's like 0, 2, 4, 6, and so on so far. Here, don't forget to include like negative part also. Minus 2, minus 0, and positive part 2. Yes, this is called even integer under addition and multiplication. It is commutative, yes, but it's no unity in here. Why? Let me show you why there is no unity in here. We know that z have unity 1, so 2z in here has an element start minus 2, 0, 2. Here we cannot find any element that suppose multiply with b, remaining the b the same. We can say this e, remaining b. We cannot find it. Yeah, we cannot find any element of e that multiply with another element of 2z gonna be remaining the same that element. So we can say this is without unity. Yeah, I hope you clear about this one. Now we move to the next part. The next part is we talking about the property of the ring. Property of ring. Suppose now we study about the rule of multiplication. It's quite simple also. Suppose we have 3 elements A, B, C belong to the ring O. Then first property is what? A times 0 equal to 0 times A equal to 0. Second property is A times minus B equal to minus A times B equal to minus AB. The third property is minus A times minus B equal to AB. And the fourth property is A times B minus C by using distributive property, and we get A times B minus A times C, and B minus C times A equal to B times A minus C times A. Yeah. Furthermore, if ring O has a unity element 1, then the property 5 says minus 1 times A equal to minus A, minus 1 times minus 1 equal to 1. Yeah, we prove that. The first proof of the property statement say A times 0 equal to 0 times A equal to 0. Now we consider A times 0. 0 we can write it as 0 times 0. Why? Because 0 is an additive identity. It's added with any element, it remaining the same. So 0 plus 0 equal to 0. We can write A times 0 equal to A times 0 plus 0. Now we using the left distributive law. Left distributive law, we multiply both of them. A, we get A times 0 plus A times 0. Now we get A times 0 equal to A times 0 plus A times 0. And one more thing, we use the same since 0 is the additive identity. So A times 0 plus 0 remaining the same. A times 0 is equal to A times 0 plus A times 0. By using cancellation law, there is A times 0 on the left part and A times 0 on the right part. We cancel them, so we get 0 equal to A times 0. So this is first part done. Now we prove the second part. 0 times A equal to 0. Now we consider 0 times A is equal to 0 plus 0. Since 0 is additive identity, it is same as above. multiplication with a. So using the right distributive law that we have discussed about it, so we get 0 times a equal to 0 times a plus 0 times a. Now we add 0 on the left side, not changing anymore because 0 is additive identity. So 0 times a plus 0 is equal to 0 times a plus 0 times a. Now using the cancellation law, cancel 0 times a on the right and left side part, we get 0 equal to 0 times a. Now from the first part and second part, we get the conclusion a times 0 equal to 0 times a equal to 0. So we done the proof of the first property. Now we continue to the proof of the second property. The second property says a times minus b equal to minus a times b equal to minus ab. Now we consider about a times 0 equal to 0 that we have discussed in the property number 1. So a times 0 equal to 0, so 0 can be written in such a way, a plus minus b. And here I would like to say something. Yeah, 0 is equal to b plus minus b. Since minus b is inverse under addition of b, so under addition both of them gonna be 0, mean identity. So 0 can be written in b plus minus b. So we get using distributive law. So we get a times b plus a times minus b is equal to 0 using left distributive law. Okay. So now we see that this is so that this part a times minus b is the additive inverse of a times b, right? Because a times minus b plus a times b is equal to 0, which is 0 is identity. Yeah. So by the definition of additive inverse, we can say a times minus b is inverse of a times b. So we can write a times minus b equal to minus ab. So we done on the first part. Now we move to the second part. Yeah. The second part of the proof property number 2 is involving 0 times 2. We have to prove this part. Minus a times b equal to minus ab. So we consider about 0 times b equal to 0. Yeah, we know that in from property number 1. So 0 can be written in such a way, a plus minus a times b equal to 0. By using the right distributive, we can write like this one. So we can see that this is form of additive inverse. By the definition of additive inverse, this shows that minus a times b is an additive inverse of a times b. So we can write minus a times b equal to minus ab. So from the first part and the second part, we get the conclusion of our property. So we have done the proof that a times minus b is equal to minus a times b equal to minus ab. Okay, now continue to the next proof of property number 3. Here nothing, we just use the previous property also. Property number 3 stated minus a times minus b equal to ab. So we consider on the left part, left hand side, minus a times minus b equal to minus bracket a minus b. Why we can say that? Since minus a times b equal to minus ab that we have done recently in the property number 2, using property number 2. And similarly, we can use property number 2 on this part also. We can write a times minus b equal to minus ab. So we get minus minus AB. So minus minus is positive, plus. So the conclusion is minus A times minus B equal to AB. Okay. Since the property number 3 is related to the property number 5. See here, property number 5. Yeah, this one. Minus 1 times A equal to minus A. Since the proof of the property number 3 is related to property number 5, so I included property number 5 proof in here also. So we need to prove minus A times B equal to minus A. Okay, how to prove that? Suppose let's say minus A times B equal to minus A. We suppose that one. So we add both sides with A. So we get minus 1 times A plus A equal to minus 1 times A plus A also, but A can be written in 1 times A. 1 is multiplicative identity, it remaining the same, no change. So we can factorizing on the right side, we factor of A, so we get minus 1 plus 1 times A, and the left side we do nothing. So we see that minus 1 plus 1 is equal to 0. Yes, 0 times A. Since we know that 0 times A by property number 1 is equal to 0. So we get minus 1 times A plus A equal to 0 by the inverse, additive inverse definition. This is so that A is a additive inverse of minus 1 times A. So we can write minus 1 times A equal to minus A. So done the proof of property number 5. Okay. Now we move to the next proof of the next property, property number 4. Property number 4 is talking about distributive law. Yeah. Now we consider on this part, we have to prove this part. So first thing is on the left part is A times B minus C. So A times B minus C. Minus C come from plus and then minus C. So we can write B plus and then minus C. So we using distributive law. So we get A times B plus A times minus C. So now we can use the second property, A times minus B equal to minus AB. So we get equal to AB the same plus minus AC. So minus and plus, it's gonna be minus. So A times B minus C is equal to AB minus AC. Done on the first part. Now we move to the second part. The second part is B minus C times A is equal to, we using the same parts of this one, minus C equal to plus and minus C. So we can write this as B plus minus C times A. So we using distributive property. So we get B times A plus minus C times A. Now we get using the second property. Yes, second property. Minus C times A equal to minus AC. Yes, this one we got it. So now we multiply plus and minus, so we get the final solution. Minus B minus C times A equal to B times A minus C times A. Now we have done proof of the first part and the second part, so proof of the 4 properties is done. Now we move to the next proof. The next proof is very easy. Well, we have to prove 6 property. 6 properties state that minus 1 times minus 1 is equal to 1. What does mean by using the property number 3? What is property number 3 say? Minus A times minus B equal to AB. So we substituting A equal to 1, B equal to 1, so we get minus A times minus B equal to minus 1 times minus 1 equal to 1 times 1, right? By using this property. So we get 1 times 1 is equal to 1. So the property number 6 is done the proof. Okay, I hope you are clear with the property of the ring. Multiplication, property multiplication rule. And now we continue to the uniqueness of unity and inverse. The theorem states that if a ring has a unity, then its unity is unique. And if a ring has a multiplicative inverse, then this multiplicative inverse is unique. So we have to prove two parts. First, if unity is unique. The second part, prove multiplicative inverse is unique. So first part, I would like to prove unity is unique. Suppose we have two elements, U1 and U2, be unity of the ring R. Then by the definition of unity, we can write A times U1 equal to U1 times A equal to 1. Since ring is commutative, yes, abelian group, so we can write this inside this way. And the second part also the same. A times U2, U2 equal to U2 times A equal to 1. What we want to get the unity is unique, we have to prove that both U1 and U2 gonna be the same. So we need to prove U1 equal to U2. Now consider to prove U1 equal to U2. Now we consider U1 equal to U1 times 1. 1 is what? Identity multiplicative. It's remaining the same. So we get U1 equal to U1 times A times U2. Since this is 1 equal to U1 times U2. 1 equal to A times U2. So we get U1 equal to U1 times A U2. Now we get using associative law under multiplication. So we get U1 times A times U2. And U1 times A is what? Is equal to 1. So we get U1 equal to 1 times U2. And 1 times U2 is what? 1 times U2 is U2. We remaining the same since U is addict multiplicative identity. So we get U1 equal to U2. Mean unity is unique. Now we move to the proof of the next part. The next part is multiplicative inverse is unique. Suppose we have two elements, B1 and B2, be the two multiplicative inverse of A. So by the definition of multiplicative inverse, we can write A times B1 equal to B1 times A equal to 1. And similarly, for A times B2 equal to B2 times A equal to 1. Now we consider B1 equal to B1 times 1. 1 is unit. 1 is what? 1 is identity multiplicative identity. So 1 can be write in such a way, A times B2. So we get B1 equal to B1 times A times B2. So since ring, all of the elements belong to the ring R. So since the ring is associative, so we use the associative law. So we get B1 times A times B2. So B1 times A is what? B1 times A is equal to 1. So we get B1 equal to 1 times B2. So we get B1 equal to B2. So the final solution is B1 equal to B2 means the multiplicative inverse of A is unique. So we done this proof also. Now we would like to continue to the next of our video. I'm gonna be talking about the subring. Subring in here, I including the definition of subring, what is the subring, and subring test also, how we identify the set is subring. Yes, we using subring test and some example of subring also. The first is definition of subring. It is an easy way to remember. The group have a subgroup, the ring has a subring similarity. Suppose we have a subset S of a ring O is said to be a subring of O. If S is itself a ring with operation of O, mean in here I can write. In here mean S said to be subring of O. If subring has operation, same operation, suppose we have multiplication and addition. So parent ring also have the same operation. No difference. Plus and minus. Let's say under addition and multiplication. So operation gonna be the same. So if the subset S belong to O, F belong to O, then S had the same operation, then we can say S is a subring of O. Now we move to the most important part is subring test. It can identify which set can be said to be a subring or something. Suppose we have a non-empty subset S of a ring O, and it's a subring of O if and only if the two conditions is satisfied. The first condition is subtraction. A minus B belong to S for all AB belong to S. And the second condition is multiplication. A times B belong to S for all AB belong to S. Now to be clear, we have some proof of the subring test. Proof of the subring test. The first part we prove of forward part. We can say forward part. Suppose we say we have S is a subring, so we have to prove A minus B belong to S and A times B belong to S. It is forward part. So now we suppose S is a subring of O. It means that S is satisfied with a sum of the ring O. So let's say there are two elements A, B belong to S. Since S is a abelian group under addition. Why? Because S is what? S is subring. Subring is what? Subring. We have to know that subring is ring. So ring is abelian group under addition. So we can mean addition A plus B belong to S. That satisfy. This property is satisfied. So we can say A belong to B or A belong to S and B also belong to S. Since the group is whole additive inverse also. So additive inverse of B is what? Minus B. So since B belong to S and S is abelian group, S is a group, so additive inverse also belong to S. Yes, that is the property of group. You have to remember that. So since A and minus B belong to S, so the addition A plus minus B also belong to S. Why? S is whole under addition. So plus of two elements of S, it still belong to S. So we get A minus B belong to S. We done the condition number 1 proof. Now we will see about the condition number 2. We have to prove A, B belong to S. Since S is a semi-subgroup under multiplication. What does it mean, semi-subgroup under multiplication? It means that it is closer under multiplication. It is closer under multiplication. So this is called group under multiplication. So suppose we have two elements A, B belong to S, so we can write A, B belong to S. Since it is simply subgroup, so multiplication also satisfied, so we can write A, B belong to S. So the condition number 2 also proved. So we done the forward part, this one also done, and we have to prove backward part. Backward part is what? Suppose we have two conditions, A minus B belong to S and A times B belong to S. We have to prove that S is a subring of O. Now let's see. Conversely, this is converse part. Conversely, suppose we have condition 1 and condition 2 hold in S, and we have to show that S satisfies a sum of the ring. If S is satisfies a sum of the ring, so S is a subring. So first we have to prove it is a ring first. How do we can prove it is a ring? Now suppose we have two elements A, B belong to S. By the condition 1, we can say A minus B belong to S. This shows that the S is a subgroup under addition, right? A minus B, we can write A plus minus B, where A belong to S, minus B belong to S, so this belong to S. Mean S is a subgroup under addition. Mean addition is whole in S. Also, S is what? S is subgroup of O, and commutative law also hold. Since the subgroup commutative law is whole under addition, there is normally, suppose we have an element A plus B, we can write B plus A. A, B belong to S. So this is commutative law whole. Then we get S is an abelian subgroup of O under addition. We get it is an abelian subgroup. Do you remember about our definition of subring? Definition of ring. Definition of ring, one important part is what? Okay, let me review that. Definition of ring. One important part is it has to hold two properties. The first property is abelian group. The first O is abelian. Sorry, it has four properties. The first is it is abelian, then it is closer under multiplication, and then it is whole for distributive law. So now we have done the second part. It is abelian subgroup. Now we move to the proof involving to associative law. So it have four property of the ring. First one is closer. Second one is associative. Third one is abelian. Abelian. Anyone abelian. And the first part is distributive law. So now we have to prove S is whole associative law. We already closer already done, abelian we already done. So we have to prove associative law. Associative law, since S is a subgroup of O, so associative law also whole in that. Since S is a subgroup. it formed to be group. So group hold under associative law. So as a hold under associative law in all, and we have done one more property on D. So the last property is we have to prove it is distributive law. Since it is similar, since it is S is a subgroup of O, then S is a group, then the group is whole for distributive law. So we can say S is whole for distributive law also. So we have done the three main part. S is an abelian subgroup under addition, as a Simbi subgroup under multiplication, and distributive law also whole. So we can say S is a subring of O. So we have done the converse part. Okay, now we have completely done the proof of subring. I hope you understand that. So we move to the example of subring. The first example is 0 mean trivial subring, and O subring of O is 0. 0 contain only one element, so we use a subring test. So 0 minus 0 equal to 0 belong to 0 itself, and 0 times 0 equal to 0 it also belong to 0. So we can say 0 is a subring of O. Yes, easy. And O is a subring of O itself. Yeah, this is interesting. O is a subring O itself. Suppose we have an element of two elements A, B belong to O. Then A minus B belong to O. Yes, since it is whole true, normally O belong to O, since O is a ring. So additive also exists belong to O. Since it is a ring, additive also exists in the ring. So we can write A plus minus B, where A belong to O and minus B belong to O. So the first condition is whole. Now consider the second condition. A times B belong to O. Similarly, since O is a ring, so multiplication also exists. So by the condition 1 and 2, we can say O is the subring of O itself. Now let me clear this one. Okay, let's move to the second example. The second example, suppose we have the set 0 to 4 is a subring of Z6. Z6 is what? Z6 is integer modulo 6. Its element has like 0, 1, 2, 3, 4, 5, only 5. Okay, 0 to 4. We have to test it is a subring or not. Suppose we use element 0 times 2 equal to 0. It is belong to 0, 0 to 4. Suppose we have 0 times 4 equal to 0. It belong to subset also 0 to 4. And if we have multiplied 2 times 4 equal to 8, and modulo 6, so we get 2. 2 is what? 2 belong to 0 to 4. So by this property, A times B belong to 0 to 4. Now we consider to the first condition, addition. So 0 plus 2 equal to 2 belong to 0 to 4. And suppose we have 4 plus 2 plus 4 equal to 6 modulo 6 equal to 0. 0 belong to 0 to 4. So we have done a plus b also belong to the subset of 0 to 4. That means 0 to 4 is satisfied with two conditions to be the subring of Z6. So it is the subring. Note that, let me clear this. Okay. It can be long. Take some time. Okay. Now let's say note others one is the unity of Z6. Yes, Z6 is including 1. 1 is unity, but unity of 0 to 4 is not the same of unity of Z6. Unity of 0 to 4 is 4. We can say 4 times 0 equal to 0. 4 times 2 equal to 8 modulo 6. So we get 2. Same. 4 times 4 equal to 16. So modulo 6. So we get 4. This means 4 is the unity. By this observation, this proves that the subring not necessary the unity of the subring not necessarily equal to unity of ring. This is the result. Result is the unity of subring not necessarily equal to the unity of the ring. Now let's consider the third example. Third example, a positive integer n and the set n z. We multiply it by n, so its element is 0 plus minus n plus minus 2n plus minus 3n and so on so far. So it is the subring of integer set. Now we can test using the subring test to prove that. We have to remember the subring test have two conditions. The first condition is subtraction and the second condition is multiplication. In this part, I explain something wrong in the first condition. For condition, we have to check a minus b belong to. Okay, sorry, I have done something wrong in here. So 4 minus 2 is equal to 2. 2 belong to 0 to 4. Now let's say let's say 2 minus 0 equal to 2 belong to 0 to 4 also. Yeah. Now let's say suppose we have 2 minus 4 equal to minus 2. Minus 2 mod 6 is equal to 4. So it is belong to 0 to 4. So we get a minus b belong to 0 to 4. Sorry that I make mistake before. I said a plus b belong to 0 to 4. It is a subring test. No, it is not. This is the correct one. The first condition. Okay, no problem. Let me clear this one. Okay, let's consider the third example again. the first condition we have to show that A minus B belong to NZ, where A, B belong to NZ also. And the second condition is what? A, B belong to NZ, and A, B belong to NZ. Okay, let's check it. Suppose I subtraction n minus 0 equal to n, it belongs to nz. Suppose we have 2n minus n equal to n, that's also belong to nz. So this means any element a minus b belong to nz. And the second property is, let's say, let's see. Okay, second property also the same. Okay, so since the Zn hold true for the property number 1, condition number 1 and condition number 2 that form to be the subring, so we can say nz is a subring of integer n. Let me say, suppose, so let me show you about the second condition. Second condition, suppose n equal to 1. So 1 times 2n, 2 times 1 equal to 2, so it is equal to 2. It is also belong to nz also. So we can say AB belong to nz. So second condition is hold, that is a subring. Now let's consider about the set of quotient integer. Quotient integer is what? In this form, we can write in this form, set I, or we can changing I to any variable like a plus b root 2. That is. This is also a subring of complex number. We know that the subring of complex number. Suppose we have a plus b I minus c plus di. So we get a minus c plus b minus d I. It is form of complex also. It belongs to set I. So it means a minus b belong to set I. Let's see the second property. It's whole or not? Okay, let's see the second property. A plus bi times c plus di. It is equal to ac plus ADI plus BCI plus minus BD. Sin I square is equal to minus 1. Complex number, complex unity. So we get AC minus BD plus AD plus BC. It is form what? I. It is form set I also. It is belong to set I. So this means A times B belong to set I. So by the first condition and the second condition hold, so set I is a subring of complex number. So that's all for this video, and this is the reference using the reference from the book Gallian Joseph in 2017, Contemporary Abstract Algebra 9 edition version, and my software using to make the slide is LaTeX. You can see that. Okay, that's all for my this video. Thank you for all of you and wish you all the best. Goodbye.